So today we're going to look at cameras and imaging and how a camera works comparametrically, photoquantographically. We're going to try to understand, what cameras measure and how television displays and so on function. So typically, the camera is part of a supply chain of visual information. So a camera we might think of the camera as, say, this black box here, and it has on the front of it a lens that emits light. The light comes in through the lens, and then it has some kind of a film plane, some kind of an image sensing plane. In this case, this camera runs on film, photographic film, that comes off of a spool. This was here called 616 film, and this type of film here was 70 millimeters wide. It's pretty much, very much like 70 millimeter motion picture film that goes on the spool. It goes over here to take up the image area, and then you take a picture and wind it onto the spool. But ultimately, the picture of the image is being printed somehow, or it's going to be conveyed to us. So there will be some kind of processing. It might be chemical processing, or it might be so on. And then there's some kind of a display here. And typically, a photograph will exist as these are photographs here of my ITAP that show its resolution capacity, the ITAP device. So we go from the sensor here through some kind of processing or process onto a display. And the display is could be photographic paper, or it could be a printed book. If it's a page in a printed book, it might be, the picture might be reproduced. This is the camera here, and overall, for example, if we look at how pictures are printed or published, this is a picture of the world's first photograph that was ever taken. That was in 1826, the world's first photograph here. And if you look closely at it, you can see these pictures that are reproduced in books are made out of tiny little dots. They're reproduced, and so they originate in some photographically and somehow appear in print. And analogously or equivalently, we may have a television camera here that captures the picture, or a kind of electrical device here that puts out an output. There's a signal that comes out of this device here, and so that camera is similar. There's a lens here, and there's a sensor array, there's an image array inside there, a Vidicon tube in this case. It's a vacuum tube that's scanned out, sensitive to light. Typically these cameras have on them, television cameras usually have the iris, but it has a C setting that's completely closed to protect the camera from damage to light. And the camera's here, and then maybe there's a television screen here. This is a television receiver, and the same thing is true. We have the image comes from a television camera here, it gets processed and it's displayed on a television screen. And typically the television screen has inside it, originally television used a cathode ray tube. This is actually a cathode ray tube inside that television. An electron beam shoots at the phosphor screen. We're actually looking in through the back. The phosphor screen's inside here, and we're actually looking through the vacuum. So the light that you're seeing actually travels through a vacuum. There's a vacuum inside here, so it's kind of like looking through the back of the cathode ray tube, and this is what a cathode ray tube looks like. There's an electron beam here, and it forms that image, and so the electron gun shoots electrons at this phosphor screen that allows us to see and understand the image. And so there's, again, another example here. There's a cathode ray screen here, and the camera comes the image comes from the camera and it's displayed on the television screen. Now, if we look inside the camera, we invariably, inside these electrical cameras, there's some kind of process happening inside here, so I'll draw it just a little bit bigger so we can delve inside it just a little bit. And then inside the television screen here, we can think of it as a process, you know, that ultimately there is some kind of display medium, which is the phosphor screen. Round in earlier televisions, you know, earlier sets, you know, often had round screens and like oscilloscopes in televisions, and then later rectangular screens started to appear. So there'll be some kind of a display mechanism here. And what we'll have there is there's a way that that display mechanism responds. There's a voltage, a time varying voltage that comes out of here. So we have an image in the television, that the rasterized image, it's scanned, the television tube is scanned across like this, and then it goes like this and it scans across and so on. And what happens is there's a time varying voltage at each point on that image plane. The voltage varies in proportion to how much light there is in some way. So when there's more light, there's, let's say, a higher voltage. And so as the light goes up higher or goes down and so on, to report the image, and then the next row of the image similarly, you know, is graphed out like this. And so the question we can ask is about how much of that light is. We can ask that question. And it turns out that television tubes, the amount of brightness that you see on the screen, or the amount of light coming off the screen, varies roughly as the amount of voltage coming in raised to about 2.22. So the quantity of light that we have coming off of here is approximately voltage raised to the 2.22 roughly. Just empirically, this is what we find when we have an electron beam and we have a grid voltage controlling it. As the voltage varies, the amount of light varies. And so televisions were placed all over the whole country, you know, the whole world. In fact, when television receivers came out, there were many televisions all over, but there would only be one television camera. Most studios in the early days just had one television camera. They didn't have multiple cameras because cameras were expensive and finicky. So they'd have one camera transmitting to everybody's television receiver. And you know, they realized that these electron tubes didn't respond linearly, that as you vary the voltage into the tube, the amount of light, I'll call that Q out, the quantity of light coming out, varied roughly in this approximately square law. Not exactly, but the amount of light coming out was approximately equal to the square of the voltage going into the tube. And so the result was that there's this kind of nonlinearity, and we say, okay, well, what we could do is we could recall all those televisions that we sold. You know, this is some function of the response, but instead of fixing all the televisions so that they respond linearly, it was easier to fix to incorporate into the television camera the reverse of that response. So much easier to build into the television camera some kind of a graph like this that looks a bit like a square root function. And so this is, let's say this is the quantity of light coming in, and this is the voltage going out. It'll look like this, and then that will go through processing and transmission and so on. In the old days, that would just go to a transmit antenna, and then the receive antenna would pick up this, and then it would go into the television receiver, which inherently had this built-in function like this. And then that went to the electron tube. Now, this is not a separate device that was built. This is just the way the electron tube responds, but I can model it. I can pretend, if you will, that electron tube here has inside it a device that, I'll draw it sort of like this as a block diagram, and then the output of that device goes into the display here. And this whole thing is the television receiver. It has that function built into it. So now we've got that whole assembly built into it, and it's transmitted the signal like this. So now what we simply do is we build this, we design this circuit into the camera, and this is called a dynamic range compressor. It tends to compress the dynamic range. The effects is that it takes fairly strong signals. If you look at strong amounts of light, it increases them. They're stronger, obviously, but it tends to boost the weaker amounts of light. So it reduces the range between the weakest and the strongest. If you look at half the amount of light comes in, it's going to produce more than half the voltage of what the full amount of light comes in. So you see here is this compressive effect where the dark signals are boosted and the lighter signals are attenuated. It doesn't make everything the same brightness, but what it does is it takes the strongest inputs and brings them down a little bit, and the weakest inputs and brings them up a little bit, so there's less dynamic range. And we call this a compressor. That's called a compressor, a dynamic range compressor. That's not the same as an air compressor that you use to blow up your tires on a car or bicycle, but it's called a dynamic range compressor, and the graph of input versus output, sort of looks like this. And typical dynamic range compressors include logarithm, square root, cube root. All of these kinds of dynamic range compressors are shaped similarly and produce similar effects. So there's your compressor built into the camera, and then, so if you look at, if we were to draw this as a block diagram inside of this camera, I would draw it that the camera has in it a sensor array, and this is kind of your traditional camera. And then after the sensor array, the output of there goes into this dynamic range compressor, which I'll just draw like this, and then that comes out, and this whole thing is enclosed in a nice tidy little box like this. And so that entire thing there is built like this. It has the lens, it has the sensor array here, and then inside the sensor array there's a circuit that compresses the dynamic range so that when it's displayed on a television it looks appealing or pleasing. It doesn't have to necessarily exactly cancel out this, but it's designed over the years. People have designed cameras so that they look good when they're connected to televisions. And so a similar thing happens with print media. If I have a photographic camera to take a still picture and I photograph something, I'll have a photographic negative, and when I develop the film I'll want it to look good. So photographic print papers are designed that have a certain response, and the print papers are designed so that they have a response that looks good on the film. And it turns out that photographic film has a similar compressive effect to dynamic range. So photographic film and television cameras are quite similar in the sense. I mean, photographic film responds approximately logarithmically to the amount of light, the density on the film over a certain range. If you look at the way that a film responds to the quantity, if I look at big Q, let's say, equals the log of little q, which is the amount of light that comes into the camera. Photographic films, often they have a sort of little region like this, and then they're linear over a certain range, and then they level off. So there's a range over which the amount of density in the film, if this is how dense the photographic negative is, the amount of density in the film will vary approximately linearly with the quantity of light. So a typical model, there's some background level alpha plus beta q to the gamma is sort of typically how these things respond in fact. And if you do a log-log plot on that, you'll see it's sort of roughly a straight line. So there's a compressive effect that photographic films tend to have, and photographic papers thus tend to have an expansive effect that undoes this effect. So when you make prints from photographs, they tend to to undo this effect here. And likewise, if you look at print media, the pictures in books, when you look at photographs in books and papers and so on, these photographs, if you look closely enough, you can see they're made out of tiny little dots. A typical photograph in a book or a newspaper is made out of small little dots. In fact, if you look at a newspaper, for example, if we just grab a piece of newspaper, newsprint, you probably see it even more readily. It's a newspaper here, and you can see in the newspaper that the pictures and images in the newspaper are made out of tiny little dots. If you look at a photograph in the newspaper, you can see it's made out of all these little dots. You can see if I come in a little closer here, you can probably see that. You can see that each image here is made out of tiny little dots. You can see them there. And in the lighter areas of the image, the ink is less present, and in the darker areas of the image there's more ink. So you can see here that the black and the white areas of the picture are made, as an image is made, there's little blobs of ink. And say in a black or dark area of the images, the blobs are bigger, and in a light area of the image, the blobs are smaller. And so the size of these ink blobs varies because newspaper is inherently digital. Print media is inherently digital. It either has 0 or a 1. It's very hard to get a little bit of ink. So either you have a 0 or 1, depending on either there's ink or not ink. It's very hard to pour ink on a piece of paper and have it be somewhere in between black or white. Either there's no ink or the ink blobs onto the paper and turns it black. So to take this digital medium, all newspapers are digital pretty well, and turn it into an analog medium, you need to modulate the dot size. You need to vary the dot size, and that's how, of course, they get these continuous tones. Now, one of the interesting side effects is when you put a little bit of ink in the newspaper. If I put some ink in the newspaper, it'll tend to spread. If I put a little drop of ink on paper, it'll spread and it'll become bigger than it was. And so what I'm aiming, if I write a graph of what the size of input and the size of the output, the darkness, let's say, the Q, let's say I'll say Q out is the quantity of light coming out, and the Q in that I want. If I put here, if I aim for a large quantity of light, I simply don't put any ink on the paper and I get a large quantity of light coming out. And if I aim for black, which is a low quantity of light, I put a blob of ink on and out comes nothing. But in the middle, if I aim for 50% coverage with ink, what happens is that the ink spreads more than I would expect. If you put a little drop of ink, it spreads out. So if I cover half the paper with ink and the other half without ink, the black ink will spread a little bit. And so the output will be darker than the input. So when I aim for 50%, I'll get something less. And if I plot a graph of what I'm aiming for in terms of how much percentage of coverage of the ink versus how much actually covers, it looks a lot like the response of a television tube. So the newsprint behaves a lot like a television tube in the way that it responds to light. And so the two of these media behave quite similarly to each other. And so you can see that they're both expansive media. They both look like a squared function, so they're both dynamic range expanders. and this is natural to television tubes naturally expand dynamic range, and so does newsprint. It naturally expands dynamic range. So in order to get a natural looking dynamic range involved here, we needed to design television cameras and photographic cameras both to produce compressive responses. Films need to be designed so that they compress dynamic range. That is to say, we want to capture a fairly large dynamic range on the film and compress it and then expand it. It expands itself when you do it in newspaper. Now in audio, people often do that. It turns out to be actually advantageous. This was accidentally discovered, that the signal processing range in television and in photography is such that we have our photographic medium here, and then we have a dynamic range compressor, and then we have storage or transmission, and then we have a dynamic range expander, and then we have the display medium. So this is display, this is expand, and this is acquisition, say, of the image or data, and then this is compress, and then this is storage and transmission. Storage is just transmitting to a future time. So this is just how the images are conveyed or processed or stored or transmitted or what have you. But so we have, this is what a camera is. A camera as we know it is an image acquisition device followed by a dynamic range compressor. And this is a TV or a display or a newspaper or whatever you want to, display medium. This is expansion and display. This happened all accidentally because TV tubes inherently have compressive response built into them, and newspapers inherently have, both of them have this expansive response built into them, for which a compressor pre-follows in a sensible way. Now, if we could it turns out that it was easier to design cameras to be compressive than it was to make the medium itself to fix these bugs in the medium. So this could be a bug or a flaw. We say that the medium's nonlinear, but actually it's a feature, not a bug. So this is really a feature of the system. And so in audio recordings, there's something called Dolby sound, which is compressing the audio. It compresses the dynamic range before you record it or transmit it, and then it expands it on the way out. In a sense, it does what's very obvious and natural and occurred accidentally in video and pictures and photography, required conscious thought or effort to do in audio. But the same thing is there, and it turns out to be advantageous to do so, to compress on the way in and expand on the way out, because it improves our dynamic range response. So now we can look at how we can really utilize that. So if we want to process images, we can undo this effect. It turns out Professor Stockham proposed that what we should do with images is we should take the logarithm and then do the processing, and then compute the anti-logarithm, and then display the image or output it. But what I pointed out to him was that television cameras and regular cameras already have a compressor built into them, and display medium already has an expander built into it, so we don't need to do this. In fact, this is what happens accidentally or normally. So what I proposed, and he called this homomorphic filtering, so I told him he was wrong. I said, instead of doing homomorphic filtering, there's already homomorphic filtering happening. What I proposed is anti-homomorphic filtering. This is, and this is what my proposal was. And what I propose that we do is we take the input from the camera, whatever's coming from the camera, and we put it through an expander, which could be an anti-log function, or it could be a square function or a cube function. And then we process the images or store them or treat them or whatever, do modifications on them, and then we run them through a compressor, and then we put them into the display television. And if we look at what that does, I'll put this tube away here in the box. If we look at what that does, I'll set these cameras aside for a moment, clear off some space. Let's look at what anti-homomorphic filtering does. What it does, anti-homomorphic filtering does, if you think about this, if you think about what's inside that camera, inside the camera there's, your sensor array is here, and then there's your dynamic range compressor, and then it comes out, and then I put a dynamic range expander here, and then I have my processor. I do my processing, machine learning, or whatever else I want to do, wearable face recognizer, my ML model, TensorFlow, whatever's going to happen, and then possibly we're done. If it's just machine learning, we're doing face recognition, we just output the name or the face. But if we're doing image processing and imaging, we may want to then take this resulting image and transmit that result somewhere. And then we pick up that result, either play it back or whatever, and then we're bringing it. What I propose we then do is that then we compress that result, and then it goes into the display. And inside the display, as we already showed, there's an expander, and then there's the display medium, which is maybe this cathode ray tube, or the print media, or the newspaper, or whatever it is, photographic prints, computer screen, YouTube video, whatever it is. This could be, it's funny, the YouTube symbol is like a tube. We used to say, what's on the tube tonight? Well, the tube is the television tube, which is the glass tube like this. So that's why we used to call it, it's on the tube or on YouTube. And so the tube is the archetype of what was the past way of seeing television. But of course, nowadays we'll see it on a flat screen display, something like this one over here. That's an OLED screen, which is quite different, but it still will mimic the way that the tubes work, because traditionally images were done in a certain way, and that's how they worked. So this is what we have, is we're gonna take this. If you'll notice, these cancel each other out approximately. If I take this and cancel that out, and these cancel each other out here, and what we've really got is a direct flow from the camera. This is some quantity of light Q. And then what comes out of here, of course, when this is not canceled out, is this is some function f of q. And this was not a bug, this is a feature f. And then what we're trying to do here with this is trying to estimate what q was, because this is really an estimate of f inverse, say f inverse hat. An estimate of the inverse of the response function of the camera. And of course the manufacturers don't like to tell you what's in the camera, but you can find out what's in the camera using comparametric equations and reverse engineer the camera and figure it out. In fact, if the camera will let you set RAW, you can do a comparogram between the RAW and the JPEG of the same image. Take a picture and save it as both JPEG and RAW, and then compute a comparogram between the JPEG and the RAW, and unravel this response function f and find the secret. Or if it doesn't have a raw function, you can take multiply differently exposed pictures and solve the comparametric equation. Now you apply an estimate of f inverse to get q hat, an estimate of q, and then we've got This is our estimate of Q, and then we're going to put another response. This is a compressor here, and then we're back to F of Q here, or some say F tilde of Q, and then over here we've got this value, we'll call this Q tilde, which is after the compression in the display, and then of course that's what's actually being displayed by this whole display mechanism here. So this is anti-homomorphic filtering, and so I hope that you've enjoyed that concept, and now let's move along to the next aspect. So I'll talk a little bit about HDR now. So let's say we have a camera here that has a certain exposure setting on it. So the camera here, and inside the camera there's a sensor array, and then it goes to this dynamic range compressor, and then out it comes out of the camera. And suppose we wish to simulate a change in exposure. Suppose we wish to double the image. So like we want to get an image that's the same as what we would have gotten if we opened this or did more exposure time. The f-stop will change the depth of field, which will change what it captures, but the actual subject matter will depend on the exposure time. So let's say we had a 1 second exposure and we wanted to get the same image as we would have when we had a 2 second exposure. So what we do here is we're going to expand the dynamic range of the image, and then we're going to multiply everything by 2, and then we'll recompress the dynamic range of the image and then output it to the television screen. So you can try this at home. For example, just take an image, and let's say a simple expander is to square every pixel in the image, double every pixel in the image, and then take the square root of every pixel in the image, and that will give you a much better looking picture than if you just double the pixel values. So this suggests a recipe for adjusting the exposure of the camera, so we can kind of consider that. Now, what if we were to have different exposures? So the way that HDR works is to extend dynamic range by combining differently exposed pictures of the same subject matter. My grandfather taught me how to weld when I was growing up, and you know, when you're welding, you look at the whole world through a dark welding helmet. Everything looks dark. But I invented this kind of new welding helmet that it's got this 45-degree beam splitter in there, and when you're wearing it, you have two cameras that are looking down, and the cameras actually fill your field of view, and I call it the eye tap, E-Y-E-T-A-P, because it kind of taps into your eye. It looks like I have glass eyes here. This is a picture of me wearing this helmet, and it looks like I have glass eyes. It looks like my eyes are made of glass, because what we have here is actually the camera lens is up here, and we're seeing a reflection of the camera lens in this beam splitter, and then there's a television display laser scanning system that scans in the image on the other side that goes into your eye. So it kind of looks like a glass eye. So we called it the eyeglass, or the glass eye, or we used to call it just glass for short. And so the way glass works is that or eye tap as we often call it, is that these cameras are looking down. You see the two cameras mounted here looking down at that beam splitter, and they capture and process those images. And the way they're processed enables us to see a dynamic range of more than 100 million to 1. We can see in the eye of the camera, we can kind of see the processed image that's coming through there. And so I want to briefly explain how that works. So let's just take one camera. There's two cameras, one for the left eye and one for the right eye. But for simplicity, let's just consider one camera at first. And so if I have a camera like this, we have the camera captures the scene, and what I did is I captured images in rapid succession. So I would take this camera and capture an image at one particular exposure. The first image, let's say, is at 1/1000th of a second. And then immediately afterwards I would grab another image at 1/500th of a second. And then immediately afterwards I would grab an image at 1/250th of a second, let's say. So I've got three differently exposed images, a dark image, a medium image, and a light image that are captured in rapid succession. For the purpose of the diagram, I'll consider the same camera at three different points in time. So I'm going to call this one here Cam 1. That's the camera at a first point in time here. And then I'm going to take a second camera and I'm going to call this Cam 2. And this is the same camera at a later point in time. And then this camera here, I'm going to call this Cam 3. And in the way I'm diagramming this, I'm going to draw it or depict it as three cameras, but it's really the same camera at three different points in time. So first we take a picture at 1/1000th of a second, then we take a picture at 1/500th of a second, and then at 1/250th of a second in rapid succession. So if we look at what's going on here, I'll kind of draw this here. I've got my camera here like this, and then I've got my next camera, and then I've got Cam 3 here. And so I have I've got Cam 1, Cam 2, Cam 3, and let's say that each of these cameras, now each of these cameras has inside it the image sensor, followed by this image compressor, and we can think of it as this one is very insensitive, so this is reporting here. So there's a certain quantity of light present before the image compressor. I'll call that Q1. And then this one we've got 2Q, or Q0 or whatever, or Q1 or whatever, 2Q1. And this one here, the quantity is 4Q1, 4 times as much. And then out here I have this unknown response function. We've got f of q, and we got f of 2q, so this we call that q1 or just q, and then we got f of 4q here. And now what we want to do is go to an estimate of f inverse, run these through an estimate of f inverse, and so we'll say that's f hat inverse, is estimate of f inverse. And out here what we have is an estimate. So this is an estimate of Q1, and this is an estimate of Q2, which is equal to 2 Q1 estimate, approximately, because there's some noise on the signal. And this is Q3, which is approximately 4 Q1 hat. These are estimates of those quantities. And so there's, if we look at a full model in the textbook, you'll see we have a full model. We've got some noise added here to the image noise NQ, and function noise NF. So we got two kinds of noise that's photoquantographic, sensor noise, and noise, for example, quantization error when this thing's quantized or digitized, and other noise sources are image-based. So some of the noise is in image space, and some of the noise is in light space. We call this light space over here, and this is image space over here. And so now we convert those images back into light space, and now you can see that we've got these multiple estimates of the same quantity, and they're differently gained. And in the darker areas of the image, what we'll find is that this camera, this picture, will give us the most information. And in the bright areas of the image, in the bright areas of the image, this underexposed image will give us most of the information, and in the dark areas of the image, this overexposed image will give us most of the information. And in fact, what we want to try to do is we'll divide this. We want to take this through a gain stage. So this is a gain of 1, this will have a gain of 1/2, and this gain will have a gain of 1/4. And now we've got 3 estimates of the same quantity Q. We've got an estimate of Q hat here. We've got 3 estimates of this underlying quantity, and then we want to combine those 3 estimates in the optimum sort of way. We weight them by the certainty functions. So we're going to take these and weight them by the certainty functions C1, C2, and C3, and then take a weighted sum, for example, and then we've got our overall estimate Q hat here, which is the estimate. This is the overall estimate here of the quantity of light from all of these quantities. So that's kind of the general idea, as we're trying to combine the exposure settings. So it's kind of almost as if we had 3 different reports of the same physical quantity. And it's like this camera is more sensitive and this camera is less sensitive, and this one's properly exposed. So we have a properly exposed image, an underexposed image, and an overexposed image, or more. We can have more estimates. We don't need just 3 exposures. But we're going to take these 3 estimates, and from these 3 estimates try to combine a true estimate of the quantity of light, and then that's the output that we display to our television screen or publish in our paper or use for our machine learning. This might go into a photoquantographic TensorFlow machine learning image recognizer, which will give us better results because it has more information about the true underlying scene. Now, what do we do for C here? These are the certainty functions. We want to understand what we mean by certainty. Measurements have associated with them a certain amount of certainty, and in just about every measuring instrument that there is, there's a notion of certainty and error. So if we get different measuring instruments here, different kinds of measurement devices here. So for example, if I look at a typical measuring instrument, there's settings on it. Like on the volts side, I can have DC volts, 1,000. I can set it to 200, 20, 200 millivolts, 0.2 volts, or 2,000 millivolts, which is 2 volts, or 200 millivolts, which is 0.2 volts. So I can set these different measurement instruments, and many of these measurement instruments have different settings, you can set them in different ways. And of course the finest instrument of them all is the PAR 124A, the best measurement instrument ever made in human history. And even this one has settings on it. You see, I can set this to, half a volt, or 0.2 volts, 0.1 volt, 50 millivolts, 20 millivolts, all the way down into microvolts and nanovolts. And the thing is, depending on where I set it, the meaning of this indicating meter, or whatever it captures, whether it goes into a computer or a moving coil meter, the meaning of this will change depending on how I set this. And how should I set this? Well, it depends on the level of the signal. You see, what you want to try and do is get this as sensitive as possible without clipping. So you're trying to get the meter into a certain range, typically. So we're trying to get this instrument, let's say, into a certain range, and so if it's too sensitive, it's going to clip and go to the end. So ideally, you know, the way that a moving coil meter works is there's a magnet in there with a little coil of wire and a spring, and it moves here, and we can have it with more gain or less gain. If we set it to a more sensitive setting, it'll go over here. Even more sensitive, it'll go over here like this, and if it's set too sensitively, it will go right over and hit the pin at the end and maybe possibly damage the unit, but if it doesn't damage the unit, at least it'll be inaccurate when it's hammered right over to the end. So what we want to do is we want to set it somehow for the signal. But the thing is, the signals, it's not just one voltage, we got a whole picture we're taking, and each pixel is in a sense a light meter. So some of the pixels are going to be brighter or more light in them, and some of them are going to be less. So we want to set, we could plot a graph of, like, say, what the pixel value is, like, let's say from 0 to 255 as most pixels go for each of R, G, and B. We could ask ourselves the question, well, if the pixel value is 0, it's completely black. We're quite uncertain what amount of light is present. It might be less than, so it's just like this meter here. If you, any of these meters, if you set it to like 1,000 volts setting and you're measuring something that's 1 microvolt, it's going to be very hard to determine what that is. We'll be very uncertain what that is. On the other hand, if it's saturated, if you're trying to measure something that's, you know, if you've got 1,000 volts coming in and you got it set to 1 volt, it's going to be saturated. It won't be accurate. So at these extremes, we know that the certainty is, it's uncertain, and somewhere in the middle it's more certain. Typically we want the reading to be higher rather than lower. So you could say a certainty function that we could assume is it's going to go up and then back down again. Typically we like the reading to be higher, so certainty functions usually, look, they're a little bit sort of lopsided like this. That's the typical shape of a certainty function that says that, you know, if the pixel values are high but not too high, we want to try to get, for each pixel, its most certain value is up here. So if we look at these different readings, if we had, you know, 3 different voltmeters going here at the same time and they each had a different setting on them, then we would be able to capture. It's kind of what I used to do in my childhood when I was recording audio. I would have, if I had a monophonic microphone, I would have the left channel turned up to 1 gain and the right channel turned up to a different gain, and the microphone coming in would go to both channels and they'd be differently gained, and have 1 loud channel and 1 quiet channel, and then take the best of both worlds as the signal evolved. So what we're going to notice is that if you look at where we are on this function, if I look at the certainty functions, if I look at the quantity of light, say here, I'll typically look at big Q equals log a little q, and I've got some light here. I'm going to have these different certainty functions that look like this, and they're going to kind of be overlapped. And so there'll be a range of light in which I want to take the brightest image over here and the darkest image when there's more light. And so the certainty functions of these images, they'll sort of be shaped, you know, they're going to be that shape. It's going to come up like this and then sharply down like that usually, and then the next one will be like this, and then the next one will be this. And so very, very bright areas of the image, we want to take them from the darkest camera exposure. They'll be most certain, and very dark images we want to take from the brightest camera exposure, and in between, something in between. We don't want to just jump. We don't want to just take the one of maximum certainty, otherwise the image looks unnatural. I have a sudden abrupt change. So usually what I do is I take a weighted sum of these depending on how much light is present. So if this, so that, let's say these are the certainty functions. So for the camera that is very insensitive to light, it takes a long time before it picks up. So this is the certainty function of, say, camera 1, what we had over here. And this camera 3, the third camera that has the high gain, it picks up pretty quickly. It becomes certain. So this is C3, and in the middle we get C2. These are C1, C2, C3. So we take this weighted sum. You know, we're going to take something like, you know, the estimate of Q1, let's say, times C1 plus the estimate of Q2 times C2 plus the estimate of Q3 times C3, and we're going to weight those certainty functions divided by C1 plus C2 plus C3, and so we're going to take this weighted sum of the certainties in order to get or calculate the actual final output image.